All right. So when we start working, let's focus, please. When we start working with vector calculus, which will be in we'll do a lot in chapter 15. We will use the dot product and the cross product in ways that it's hard to even imagine now. They will become very, very familiar. We'll be doing dot products and cross products as parts of much bigger problems. But now we're just talking about the dot product and the cross product as a thing, and that's all we're doing. So the cross product is just a second form of vector multiplication. You will also hear the cross product called the vector product. In contrast with the dot product, which is also known as the scalar product. And I'm going to write out the definition of the cross product. So if we have two vectors, u1 I hat plus u2 j hat plus u3 k hat, and v, write out our components. U cross k, or sorry, u cross v is, this is going to be kind of a long, u2, long, messy thing, u3 v2 I hat minus u1 v3 minus u3 v1 j hat plus u1 v2 minus u2 v1 k hat. And you'll notice that each of these terms, there's only the j and the k components here, the I and the k components here, and the I and the j components there. What's that? Yes, that's a v. Cross products are only defined for three-dimensional vectors. And we'll talk about why in just a second. Well, actually, the reason that the cross product is only defined for three-dimensional vectors is that u cross v is orthogonal to both u and v. So if you have two vectors in the plane, the cross product is going to be orthogonal to that plane. So two vectors in the xy plane, if you take the cross product of those two, you get a cross product in the direction of the z-axis. So that's why we only define the cross product for three-dimensional vectors. Now, this is a messy, kind of difficult way to visualize finding the cross product. There's an easier way that we do the cross product, and usually that's with what we call the determinant form. And I'm going to say I usually use the determinant form. So we would write the determinant I hat, j hat, k hat, u1, u2, u3, v1, v2, v3, the determinant of that matrix. So U cross V is equal to that determinant. This is not really a determinant because we have this is kind of an ill-defined matrix with the I hat, J hat, K hat in there. But the form of the determinant helps us remember how to do it. And just as a quick reminder, we'll do a couple of examples. The determinant for the I hat component, we would cross out this column and this row and find the determinant of this 2 by 2 matrix, U2 V3 minus U3 V2, which is exactly what we want here. We remember that the second term is negative. It's always negative. And then we cross out this column and this row, and we do U1 times V3 minus U3 V1. And then we do the plus the K hat, cross out that row and that column, and do the determinant of that 2 by 2 matrix. I strongly recommend that you write out either in some kind of way the shorthand here, because it's very, very easy to make an arithmetic error, especially a sign error, plus minus error, when you're evaluating determinants. All right, so let's do a quick example, and then we'll talk about some properties. The cross product has several very important geometric properties that we will take advantage of a lot in second semester. So let's say that U is the vector 1, -2, 1, and V is the vector 3, 1, -2. And we want to find U cross V. So we're going to say that U cross V is this determinant, I hat, J hat, K hat, for our first row. 1, -2, 1, 3, 1, -2. And I'm going to write out, so I always write it out explicitly because I make arithmetic errors, I make sign errors. So I always write it out. So this is I hat times -2 times 2, which is 4, minus 1 times 1. Second term, negative, minus J hat. That term is always negative. And we're going to cross out this column in that row. So 1 times -2. Did I do that right? Yes. I just want to make sure I wrote this down correctly. 1 times -2 is -2 plus, or sorry, minus 3. 1 times 3. And then plus K hat times, we'll cross out that row on that column, find that determinant, 1 minus -6. So we end up with 3 I hat plus 5 J hat, so it's minus 5, and then we've got a minus there, and then a 7 K hat. What would we do next if the problem said, and verify that U cross V is orthogonal to both U and V? What would we do? Dot product. We do the dot product of this with U and the dot product of that with V, and we should see that they're both equal to 0. When on Friday, when we start talking about planes in space, the equations of planes, what is going to be important, a key piece of information about a plane in space is the vector that is normal to the plane. So we might need a unit vector that's normal to a plane, and we might be able to use the cross product to find that unit normal vector. All right. Algebraic properties. Algebraic properties of the cross product. One is that u cross v is the negative of v cross u. So we say that the cross product is anti-commutative. So the order that we do the cross product in matters, because we'll get a vector pointed in the opposite direction.
It doesn't really matter. It's the same.
It's a same magnitude. So what the other way that we can say this is that 3 by 3 matrices form a non-abelian group.
Okay.
Got it. U cross U plus W. We can distribute a cross product as long as we pay attention to the order. Sorry, this should be a V. U cross V plus U cross W. We have to maintain the original order of the multiplication. We can't switch around the order, but we can distribute. A scalar times a cross product is the scalar times either of the vectors crossed with the other. The zero vector crossed with any vector is the zero vector. Cross product is a vector. Any vector crossed with itself is the zero vector. And then there's this special product, V cross W. Is the same as U cross V dot W. And we call this the scalar triple product.
Oh, of course. Oh, yeah. I remember that.
Or the box product. The box product. And I'll explain why it's called the box product in just a minute. Yes?
The one where you said the U or the zero vector cross the U vector. Isn't it that the cross product is always orthogonal to those vectors?
Right.
So how is the zero vector orthogonal to itself?
Zero vector is orthogonal to every vector.
Oh,
Yeah, including itself.
Whoa, that's crazy. Because when you take it, because if it's orthogonal to one vector, it must be parallel to another. You could draw another vector in the same direction. Or is it just that magical nothing void that is always orthogonal to the vector?
Yeah, zero vector is always orthogonal to every vector.
That's not okay.
All right. So these are algebraic properties. Let's talk about the geometric properties. The geometric properties are the ones that are going to be important that we're going to use in Calc 3 a lot. The geometric properties. I'm going to say theta is the acute angle between U and V. Our first property we already talked about, U cross V. This is one of the most important ones, is orthogonal to both U and V. So that's one of the big ones that we are going to use. We want that orthogonal vector. The magnitude of u cross v is the magnitude of u times the magnitude of v times the sine of the angle between them. So similar to the relationship we had with the dot product, but this has a sine theta, and we're talking about the magnitude since the cross product is a vector. U cross v equals the 0 vector if and only if u and v are scalar multiples of each other. And what's that another way of saying?
They're the same
They're
vectors.
parallel. So our cross product is 0 if and only if the two vectors are parallel. So this gives us a way to test for parallel vectors. Now, scalar multiple is usually an easier way to test, but the cross product, if we know the cross product is 0, that also tells us that the vectors are parallel. This next one is another one that we will take advantage of quite a bit next semester. The magnitude of u cross v is the area of the parallelogram with u and v as adjacent sides. So what we're saying visually here is if I have two vectors, there's u, oops, I wanted an arrow on there. I wanted that, there we go. There's u and there's v. If we turn this into a little parallelogram, like so, the area equals the magnitude of u cross v. And the reason for that is we said that the magnitude of u cross v is u times v times the sine of theta. This height is u sine theta, magnitude of u. Sine theta. So that's the height of the parallelogram. Multiply the base times the height, and we get the area. So what we end up doing in second semester is we will talk about, we want to figure out areas of surfaces. And what we'll do is find two vectors on the surface, maybe two vectors in a particular direction, find the cross product. The magnitude of that cross product is approximately the area of the little surface at that point, and we'll integrate that cross product over the surface to find surface area. So we're going to use cross product as an area. And finally, this one it doesn't get used as much, but it comes up very occasionally. And we'll like this word, u dot v cross w, our scalar triple product or a box product, is the volume of the parallelepiped
He's making up words.
Mr. Beamer.
with u, v, and w as adjacent sides. And this is just a box.
Okay. Why did we call it? Just to, why did we say you're not? Just a class. Whatever. No, I'm gonna write
All right, so what we're talking about here is if we have a shape like this, there's two vectors in the plane, and if we form a box out of this shape, something like,
Oh, so we literally, it's just it's a square.
not a square, because the base, not rectangular, parallelogram prism. The base is a parallelogram.
So it's a parallelepiped.
Yeah, a parallelepiped is a prism with a parallelogram as the base.
Can it be parallelograms on all the sides?
Yes.
So it could be like a parallelogram, but then also not.
Yeah. So it could be just like a right. It could have it can be a squashed box.
Yeah, that just looks like a box.
Oh, that's just a box.
Well, here, I'll do this then.
It's like a rectangular. Oh,
A rectangular prism is a subset of a parallelepiped.
the parallelepiped is not a subset of it.
Right. So I could do it this. I could make this side go this way. So I wanted this. Now I want this. Yes. Like so. And then all of our sides.
What's your problem?
All of our sides are parallelograms.
I can now visualize that.
So this is a slanted box.
It could be very slanted or not.
Yeah.
It's like you have a box.
It's a slanted
You're
box.
missing a side.
Oh, thank you. There we go.
There we go.
So the box product or the scalar triple product is the volume of that little shape. If this is U, V, and W. So that's why we call it the box product, because it's the volume of that box. So you could, in theory, you could integrate, you could use the scalar triple product to find the volume of a shape, and you could integrate that over some solid shape to find the volume.
It's like a block.
Yeah, it's a squished box. All right. Last question, last example. We're not going to go all the way through this. I just want to ask you this question
Oh, jeez.
and how we would go about this. Find a unit vector. Orthogonal to both A equals I hat plus 2 j hat minus k hat, and B, vector B equals negative 2 I hat plus 2 j hat plus 2 k hat. So we're not going to go through the process, but let's talk about the problem solving procedure. What is this in what's another way that this question could be asked?
Find cross product and then multiply it times by standard.
Right. We could say find U A cross B over the magnitude of A cross B. The other way that that you may be asked this question, it might say normalize normalize A cross B. So normalize is the process of finding a unit vector in the direction of that thing. Could we also use B cross A?
You'd have to flip it
You have to multiply by -1. So it
Yeah.
takes
But would it matter?
Could, no, it would just be the other way.
Yeah, it would just be the other way. It would still be orthogonal, right?
If the question doesn't specify, so for example, if we were asked it in the first way, either way would be acceptable.
Right.
Because the other two tell us
Right,
to cross B.
right.
The
If
first
this gives us a specific order.
where the first one just
Right,
even
just
if they're A
ask
and
us-
B, and
right.
most people probably do A and B, there's nothing incorrect about doing it B than A.
All right. So since we weren't here on Friday, do you know what you get when you cross an elephant and a banana?
Vanelephant. No, it's a vanelephant.
Elephant, banana, sine theta.
Yes. Yes, it's a vanelephant.
Do you know why the vector crossed the road? To be normal. All right. Yeah, Michael.
What do you get when you cross an elephant and a mountain climber?
An elephant and a mountain climber?
You can't cross a vector.
You can't cross a vector with a scalar.
You can't cross a vector with a scalar.
I realize that you're drawing.
Can you vectorize a scalar? Like make a scalar into a vector?
So,
You could make a scalar with that particular magnitude, I guess.
Can you make a vector in that it's x to the
why don't
some
you just do
direction?
7 through 17 odd?
Yeah, and why?
Set 3, 5, 7, 9, 11. Just it's fun to write all those numbers.
Well, no, it's like we had make sure we wrote all those segments so we got the opportunity to cross.
Well, I could. How about this? 3 through 17 odd.
No, 5.
Skip 5.
There you go. I like
No, not skip 5. Skip number 5. Because I know you would all take that literally.
it. Well,